Good morning. Today we are gonna study the infrared spectroscopy, the theory behind this characterization technique, and also some of their applications. Okay. Among all the instrumental methods for structure determination, there are these few that you already know and have worked with. First of all, we have the nuclear magnetic resonance. In this one, the excitation of the nucleus of atom through the radiofrequency high irradiation provides the extensive information about the molecular structure and atom connectivity. Also, the infrared spectroscopy use targeting molecular vibration through irradiation with infrared light to provide mostly information about the presence or absence of certain functional groups. Mostly it is used most commonly for organic compounds or covalent bonds, right? Then mass spectrometry. In mass spectrometry, the sample is bombarded with electron and the detection is resulted from the molecular fragments that are formed from the molecule. It then provides information about the molecular mass and atom connectivity because we can study the fragments, the molecular fragments that are produced from this electron bombarding, and then we can make assumptions or study the connectivity that from between each of these molecular fragments, and to build a skeleton from this information about the molecule, right? And the connectivities. The ultraviolet spectroscopy uses the promotion of electrons to higher energy level through irradiation of the molecules with ultraviolet light in order to provide mostly information about the presence of conjugated p systems and the presence of doubles and triple bonds. Specifically, the infrared spectroscopy deals with the interaction of infrared radiation with matter, right? The IR spectrum of a compound can be provided with important information about its chemicals, nature, and the molecular structure. It is most commonly used to measure the absorption used by measuring the absorption of the IR radiation, and through infrared emission and reflection is also used. It is widely applied in the analysis of organic materials, also useful for polyatomic inorganic molecule and organometallic compounds, but mostly is used for to study covalent bonds. In this case, the electromagnetic radiation is a radiant energy having dual properties of both waves and particles. The particles of the electromagnetic radiation are called photons, and each has a discrete amount of energy called quantums. Also, the energy in electromagnetic radiation can be characterized by its wavelength and frequency. We are gonna see this more in detail later on. The wavelength is the distance from one point on a wavelength to the same point on an adjacent wave. The frequency is the number of waves passing per unit time. It is reported in cycles per second. It is -1 second, or over second, which is also called hertz, right? And the energy is directly proportional to the frequency and inversely proportional to the wavelength. We are gonna see this in detail later on. As we can see here, you can use some different units to report the wavelength, right? All are units of distance. Meters, centimeters, micrometers, nanometers, and angstroms. And this is the conversion to meters. As you can see in this diagram, when you move from a lower frequency to a higher frequency, the wavelength is inversed, right? You have here is the wavelength and here is the energy, right? Since the frequency and the wavelength are inversely proportional, whenever we have a lower wavelength, we will have a longer frequency and vice versa. The same with the wavelength and the energy. Because remember, frequency and energy are directly proportional, and wavelength and energy are vice versa proportional. The same with wavelength and frequency, right? So, as you can see here, you have in this diagram the spectrum of wavelength from radio to gamma rays and the effects of this electromagnetic radiation on molecules, which is shown in green. And here, as the energy is increasing in blue, as you can see, the wavelength is getting reduced and the frequency is increasing because this wavelength and frequency, as I mentioned, is vice versa proportional, inversely proportional, I'm sorry. And the molecular effects are, in radio, occurs a nuclear spin transition, microwave rotational motion. In molecular vibrations, molecular vibration happens when infrared energy is irradiated to the atom or to the molecule of interest. Electronic transition for near UV and even visible. Then with vacuum UV, X-ray, and gamma rays is when ionization takes place. As you can see from this diagram, the light that our eyes sees, which is the visible light, the visible region, is but a small part of the broad spectrum of the electromagnetic radiation. On the immediate high energy side as we see here, the visible spectrum lies the ultraviolet, and on the low energy side is the infrared. Then the portion of the infrared region, as you can see here, that is most useful for analysis of organic chemistry, that is an interesting information, is not immediately adjacent to the visible light, but is that having a wavelength range from 2,500 to 60,000 nanometers, with a corresponding frequency range that I will show further, right? Always in gigahertz. And all the different forms of the electromagnetic radiation is what makes up the electromagnetic spectrum. All the electromagnetic spectrum. And this is what we only see. Now, we will come with the formulas to understand understand better how the relationship between energy, wavelength, and frequency, right? As we can see here, we have the relationship between wavelength and frequency. Wavelength and frequency is going to be the speed of light. And from this equation, you can realize that frequency and wavelength are inversely proportional. Then we have the energy formula of the one of the most important formula in electromagnetic radiations to study or to quantify electromagnetic radiation, which is energy is going to be equal to the Planck constant times the frequency. And from here, you can come out with the conclusion that the energy and the frequency are directly proportional. And by correspondency, then the energy and the wavelength are inversely proportional as well. As you can see here we have C, and here we have the wavelength, the representation. The infrared radiation, as I was mentioning before, goes from a wavelength between 2.5 to 17 micrometers, with a corresponding frequency of 4,000 to 600 centimeters, 1/centimeters, right? These frequencies match the frequencies of covalent bonds stretching and bending vibration. Hence, the infrared spectroscopy can be used to find out about covalent bonds in molecules. From DIR, we can answer two key questions that are mostly what type of bonds are present, and we can also come out with some structural information from the type of bonds that we have in the molecules. From the energy formula, we can also determine that by having a delta energy is equal to Planck constant versus frequency class, which is also going to be equal to Planck constant over 2p and the square of spring strength, which is the bond stiffness, is directly related to the bond stiffness, and the reduced mass of the atom. So from here, we can understand that the frequency depends mostly on the reduced mass and the bond stiffness. And more specifically, the frequency is going to be directly proportional, as you can understand from the formula, to the strength of the bonding between the two atoms, and is also inversely proportional to the reduced mass of the two atoms. These are a few examples of distribution frequency and how it depends on the atomic masses and the bond energies. As you can see here, from CH, CD, and CC, we go from a lighter atom and to a heavier atoms, right? And the frequency dependence is as follows, right? The frequency is going to be reduced since the atom mass is increasing, and as you can see, the bond energy is getting reduced since it is directly proportional to the frequency that is also getting reduced. depending on the bond independence of the bond with the bond's energy. As you can see here, we go from a an atom, a single bond, carbon-carbon single bond, to triple bond. As the energy is increasing, the bond energy is increasing, the frequency is also increasing, since the energy and the frequency are directly proportional, and the bond energy as well is directly proportional to the frequency, right? As a conclusion, the frequency decreases with the increasing atomic weight, and the frequency increases with the increasing bond energy. In this diagram with C, we can understand that the infrared radiation is largely a thermal energy that induces the stronger molecular vibration in covalent bonds, which can be viewed as a spin holding together two masses or atoms, right? There are specific bonds respond to absorb specific frequencies, right? As you can see here is the equilibrium bond length, and this is when it is stretched and when it is compressed. And this movement, this bond movement caused by the IR radiation absorption, is what is reflected in the IR spectrum, right? We have three different vibrational modes, including stretching, rocking, and seesaw. I'm sorry for the English. The most useful band in an infrared spectrum correspond to the stretching frequency, and those will be ones we will focus on. Here is a symmetric stretching, anti-symmetric when one bond is being compressed and the other one is getting stressed, and the bending vibration, right? When the length is getting constant, but the angle is changing, right? When these atoms, let's say that these atoms are moving symmetrically to a imaginary center that is with the center atom. Then the IR radiation does not have enough energy to induce electronic transition as we see with the UV, and if the frequency of the radiation matches the vibrational frequency of the molecule, then the radiation will be absorbed, generating or causing a change in the amplitude of the molecular vibration. Then the higher spectrum are most commonly presented as percent light transmitted through a sample as a function of the wavelength or the energy of the light. Samples that absorb all the higher light will give a spectrum with an horizontal line near the bottom of the spectrum. How does it work? Right. You have the IR source, you have the chemical sample, and you have a detector. When the IR source irradiates the sample, some energy is getting absorbed, or wavelength or frequency is getting absorbed, and the other is getting transmitted. Then the detector gets the signal from the difference between the irradiated source and the transmitted light that is getting detected, right? This difference is going to be the absorbed energy, and will give the signals for the specific chemical sample, right? Some light can also be reflected back to the source, and depending on the technique, the detector will detect the transmitted light or the reflected light. And from all the frequencies that the sample receive, the chemical sample will absorb those specific frequencies that that match with that depends on the specific bond types or functional groups that the molecule has, and the rest will be transmitted and will arrive to the detector. You can see here an example of an IR spectrum in an absorption mode. In this case, the IR spectrum is basically a plot of transmitted or of absorbed, frequency versus the intensity of the transition or the absorption. In this case, the frequencies will appear in the x-axis in units of inverse centimeter, and the intensities are plotted on the y-axis in percent units, right? This is an absorption mode, and this is a transmission mode. In here, this is the most commonly IR spectrum that is the most commonly used for represent the IR spectrum of a molecule. That is going to be found in most of the chemistry and spectroscopic book, also in the research papers or manuscripts, and therefore we will use this representation in our um, in our characterizations when we characterize all these samples in all these steps for this synthesis, right? The bands can be classified as a strong, medium, or weak, depending on their relative intensities in the infrared spectrum. A strong band will cover most of the y-axis, as you can see here. One example of this strong band will be the carboxylic, the C double bond O band. Then a medium band falls to about half of the y-axis, and an example can be the NH stretching, the OH, and others. Then finally the weak band falls about 1/3 or less of the y-axis, and we can see as an example the benzene fingerprints of a specific molecule, right? This is very important to know that not all covalent bonds display bands in the IR spectrum. It means that not all covalent bonds or not all molecules are infrared active. Only polar bonds will do so. And these are referred to as IR active molecule or IR active bonds. The intensity of the band depends on the magnitude of the dipole moment associated with the bond in question, right? Strongly polar bonds such as carbonyl group CO produces a strong band, as we mentioned before. The medium polarity bonds and asymmetry bonds will produce medium band, and weakly polar bonds and symmetric bonds will produce weak or not observable band. As you can see here, the carbonyl group will show a strong band, it's very polar functional group. A medium one will see the CN or sign nitrile. A weak signal will be shown in imines, ethenes, and all these triple bonds that have a low dipole moment. And as this one is very symmetrical and no polar, and this, for example, this signal from this molecule is not going to be observable. The infrared band shape is another feature that will take our attention when analyzing an IR spectrum. They can be narrow and broad. Narrow bands are thin and pointed like a dagger, and broad bands are wide and smoother, right? A typical very well-known example of a broadband is that displayed by the OH bond, such as those found in alcohol and carboxylic acids, and as shown below. Right, it's a very broad band, very intense, and then what is the information that we can obtain from the IR spectrum, right? IR is most useful in providing information about the presence or absence of specific functional groups. Hence, IR can provide a molecular fingerprint that can be used when comparing samples. If two pure samples display the same IR spectrum, it can be agreed that they are the same compound. IR does not provide detailed information or proof of molecular formula or structure. It provides information of molecular fragments, specifically functional groups. Therefore, it's very limited in scope and must be used in conjunction with other techniques to provide a more complete picture of the molecular structure, such as NMR and mass spectrometry. From here, we can understand that when using IR spectroscopy to analyze or characterize a molecule, from there we will get the most important functional groups. This IR spectroscopy is very useful in analyzing or comparing starting materials versus product, or analyzing also the progress of a reaction when other techniques, easier and cheaper techniques are not available or suitable for a specific reaction. If you see a difference between the starting materials and the product, functional groups that are appearing in the product or are disappearing in the product in comparison with the starting material, then we can understand that reaction. Also, we can if we run IR versus time from a specific reaction, we can understand also, it can help us to understand the mechanism for this reaction, and also with the help of other specific techniques, as I mentioned, NMR spectroscopy and mass spectroscopy, which are the most commonly used in organic chemistry. We can provide a whole picture of the molecule, and we can make sure that the molecule that we were intending to synthesize is actually there. As I mentioned, we have then fingerprint regions for the different functional groups, right? In the region from 1,500 to 400 inverse centimeters, vibrational frequencies are affected by the entire molecule, as the broadest ranges for our absorption in the figure below, which are the fingerprint regions, right? Absorption in this fingerprint region is characteristic of the molecules as a whole. This region finds widespread use for identification purpose by comparison with library spectra. And that's how you analyze the spectrum. You get your compound, then you analyze your more intense or important bands, generally the ones that are more easily to identify or to compare with the literature, and then you determine what functional groups is present in your molecule. In this zone, in the higher frequency, we will find generally broad signals that will be due OH, NH, CH stretch. Also, we will find Z triple bond C and Z triple bond N stretch, which are going to be much less intense than the previous one. In this intermediate region, we will have very intense signal, that is ZO stretch, CN stretch, and ZC stretch. These are going to be less intense. And also we will have the NH band, that is also very intense. CH band, also OH band we will have. In this region, we will have the C single bond O stretch, the CN stretch, the ZC stretch, and in this lower frequency region, then the NH band and CH band, right? In here is the fingerprint of the molecule. It means that if you get this exactly the same spectrum with a reference in comparison, you can easily understand or determine that you are talking about the same molecule. And in this region, is mostly to identify the most important functional groups, as we mentioned before. Through the entire IR spectrum can be used as a fingerprint for the purpose of comparing molecules. The 600 to 1400 inverse centimeters range is called the fingerprint region, as we mentioned. This is normally a complex area showing many bands, frequently overlapping each other. This complexity limits its use to that of a fingerprint, and should be ignored by beginners when analyzing a spectrum. Since this is a very complex region, if you get exactly the same signals on the same spectrum, it overlaps with other spectrum that you have from reference, then you're talking about the same molecule. You must focus as a student in this region, mostly in the functional groups region, and you should practice yourself analyzing this type of spectrum in order to identify each of the functional groups that are present here, right? For example, this is the spectrum of 1-butanol. Here, this is the OH strength. This is the first signal that I look for in this type of compounds. And then, as you can see here, is the saturated CH, right? The CO stretch is unreliable here, as you can see. So it is not determined in saying that you have CO bonds in there, right? You cannot easily say, yes, I have here a CO bond, because it is not clear since it's overlapped with other signals. Here you see again the where the following types of bonds normally absorbed. As we mentioned before, NH, OH, CH are going to absorb in this region. C triple bond C, C triple bond N are going to absorb in this region, small region over here. The C double bonds C, C double bond O, C double bond N are going to absorb in this region, and in this fingerprint region, all these bonds, C simple bond C, CO, and CN. Specifically, alkanes have no functional groups, right? So when analyzing the spectrum of an alkane, the IR spectrum display only CC and CH bonds, right? Of these, the most useful are the CH bonds of here that will appear around 3000 inverse centimeter. See, most organic molecules have such bonds. Most organic molecules will displace those bonds in their spectrum. But for example, when having an alkane, an hexane spectrum, IR spectrum, you can look for other type of functional groups to determine if it is not the molecule. You can say, at least this looks like an alkane since only displays CH stretch signals and CH bending signals. But it is hard to determine what type of alkane it is. So it is only a complementary characterization technique. In the case of an alkane, right, also shown a sharp medium band corresponding to the C double bond C bond stretching vibration, as here in here. And some alkanes may also show a band for the double bond then C and simple bond H when are terminal alkanes, right? Appearing around 380 inverse centimeters, right? As you can see here. However, this band could be excluded by the broadened band appearing around 3000, right? For example, if it has a functional groups such as OH that we are gonna see now. But in this case, if we have an alkane, a terminal alkane, we can determine it by looking at this specific band over here. This one, for example, is also example in which this CH stretch can be occluded or hidden behind or be within other signals such as the CH stretch, right? This is the cis-2 octane. It can be occluded and it cannot be easily identified. In this case, this is the CC stretch, right? And also, I forgot to mention that this is most easily identified when you have a terminal alkene. It means C in which this carbon is one of the carbon is only bonded to hydrogens. It is generally separated and easily to identify this signal. But in case, as you mentioned, as you saw here, of more substituted alkane, it gets harder to define which one is these signals, right? In the case of alkenes, the most prominent bands correspond to carbon-carbon triple bond. This is shown as a sharp, weak band around 2100 inverse centimeters. The reason it's weak it is because the triple bond is not very polar, as you may know. In some cases, such as in highly symmetrical alkyne, it may not show at all due to the low polarity of the triple bond. Terminal alkenes, that is to say those where the triple bond is at the end of the carbon chain have a CH bond involving the sp carbon, the carbon that forms part of the triple bond. Therefore, they may have also shown a sharp weak bond around 3300 inverse centimeter, corresponding to the CH stretch. Internal alkenes that in those where the triple bond is in the middle of the carbon chain do not have a CH bond to the sp carbon, as therefore the lack of the aforementioned bond. Now we are going to see an example in a comparison between a non-symmetrical terminal alkene, 1-octene, and the symmetrical internal alkene, 4-octene. As you can see here, right? This stretch in the non-symmetrical or the terminal alkene will show this stretch line. And as you can see over here, you cannot see this stretch line, right? It is because, as we saw, and I want to emphasize the terminal alkene have CH bond involving the sp carbon, right? The carbon that forms part of the triple bond, right? And it can be seen in this region. For the terminal or unsymmetrical alkene, and for the symmetrical, you don't see. See, and this also in this region as well, the CH stretch signal is very easily to identify this signal, since it is very sharp and intense. And in asymmetrical you cannot see as well. In the case of the CN triple bond, this bond has a sharp pointed shape, just like the alkyne CC triple bond. But because the CN triple bond is more polar, this bond is stronger than the alkane. Then is when you have the spectrum is getting more complex, right? But because you can think that you are getting an alkene or you are getting a CN triple bond. If you have mixed and you can, and you don't easily identify all the signals that you are available in that you have available in the spectrum, or if you don't have another technique to help you to conclude about the molecular form linkage that you are identifying a product, then it is more complex, right? Because you have signals that can be confusing. In this case, this one is more intense, right, than this signal over here, but it can be confusing. The most prominent band, as you can see here, are the OH bonds. It's a very broad and intense signal, and it appears it will cover about 3,000 to 3,700 centimeter inverse centimeter. The sheer size and broad shape of the band dominates the IR spectrum and makes it hard to miss, right? It is easily shown even when you have a spectrum that contains water. It can be also confusing. It must be very dry in order for you to not have these signals. That's why the most precise IR spectrum are on the nitrogen atmosphere in order to reduce the amount of water in the sample as much as possible, even if the water is hygroscopic and can absorb water from the air, or if the air is humid, it generally can show a OH band due to water if it is not properly handling the sample, and also if you don't have an inert atmosphere inside the IR spectrometer, you can also see in some cases DOH due to water. This is an example of one butanol, and this is the saturated CH stress. And here in the as we saw, this is the fingerprint flow, and the COH strength is unreliable. You cannot easily identify that signal. In general, carbonyl compounds are those that contains the C double bond O functional groups. In aldehyde, this group is at the end of the carbon chain, whereas in ketones, it's in the middle of the chain. As a result, the carbon in a carbonyl bonds of aldehydes is also bonded to another carbon and hydrogen, whereas the same carbon in a ketone is bonded to two other carbons, right? Aldehydes and ketones show a strong prominent shaped band around 1710 to 1720 inverse centimeters, right in the middle of the spectrum. It is a very intense and hard to miss signal. This band is due to the high polar carbonyl group. Because of its position, shape, and size, it is hard to miss, as we said. Because of the aldehydes also contain CH bonds to the sp2 carbon of the CH bond, they also show a pair of medium strange bonds positioned about 2,700 and 2,800 inverse centimeter. These bands are missing in the spectrum of a ketone because of the sp2 carbon of the ketone lacks the CH bond, right? These following slide we are gonna see a comparison between aldehyde and ketone. As you can see here, this is a butylaldehyde, right? And as you can see, this is the signals that are due to this saturated CH stretching, and also the CH stretch over here. The CH CH stretch, this CH stretch over here, right? In this is the CH stretch bond that is in 1720, and in the ketone you will have this same signal over here, but you are not going to have this CH signal over here that is due to the sp2 carbon that is bonded to a nitrogen, right? In this region, you are not going to get this signal. That's how it makes kind of easy to identify or differentiate between an aldehyde and a ketone. That is, in this case, the heptanone. In a carboxylic acid case, these functional groups combines the features of alcohol and ketone because it has both the OH bonds and the carbonyl group carbonyl bond. Therefore, the carboxylic acid shown a very strong and broad band covering a wide range between 2,800 and 3,500 inverse centimeter for the OH strength. Whenever you see this very broad band with also has the CH stretch inside generally that occludes all this region, you can make sure that you have a carboxylic acid there. At the same time, they also shown this steak-shaped band in the middle of the spectrum that correspond to the carbonyl group, right? In this case, you have in the literature the typical frequencies for a carbonyl group that is due to the carboxylic acid, that is due to the that is because that is in a ketone or is in the aldehyde. They have different typical frequencies or wavelengths, right? In the case of the amines, the most characteristic bands are due to the NH bond stretch. Since it will appear as a weak or medium and somehow broad band, but not as broad as OH for a band for alcohol. This band is positioned at the left of the spectrum in the range of 3,200 to 3,600 inverse centimeters, as you can see here. This spike is very typical of the amine. Since primary amines have two NH bonds, therefore they typically show two spikes that makes this band resembles a molar tooth. Right? That's in here. Secondary amines have only one NH bond, which makes them show only one peak, resembling a canine tooth. Finally, tertiary amines have not an H bond, and therefore this band is absent from the entire spectrum altogether. This is the secondary amine, right? It's only one peak here, since it has only one NH bond. In the case of amide, you will see in the NH part will have since it will combine features from both the amine and the ketones, or I mean the carboxylic group. Amide will show a very strong peak and kind of broad at the left of the spectrum in the range between 3,100 and 3,500 inverse centimeters because of the NH stretch, right? At the same time, they also show the state-shaped band in the middle of a spectrum, around 100 and 1,710 inverse centimeter for the carboxylic stretch. As with the amine, primary amine shown two peaks, whereas secondary amine show only one peak here. This is because of the primary amine will have two NH bonds, and secondary amine will have only one NH bond here. This is an example of a primary amide. This is going to be all for today's class. I hope you understood everything regarding the IR spectrum, the theory, and how to interpret and delucidate the IR spectrum for your molecular compound. This is very important for you to understand in order to characterize all the products that you are getting in all the synthesis, right? Again, this information goes more in deep in the case of in your book, and you can find more information in this literature and also in other important literatures in the internet, right? Again, if you have any doubt or need any help regarding this matter or this content, you can reach me at my email. I hope you all have a great week and see you soon. Bye bye.